Hello students, in today's lecture we are going to solve NCERT exercise problems from 11.1 to 11.11 on dual nature of radiation and matter. This is disclaimer. Learning objectives. After this lecture you will able to understand and apply concepts photoelectric effect, X-rays production and de Broglie wavelength through numerical problem solving. Then calculate and analyze various quantum phenomena parameters like frequency, wavelength, kinetic energy, stopping potential and work function using relevant formulas and relationships. So in today's lecture we will cover NCERT exercise problems on dual nature of radiation and matter. There are total 11 questions and we are going to cover all questions. Alright. So, find the maximum frequency and second minimum wavelength of X-rays produced by 30k volt electrons. It means 30 kilovolt electrons. Let's see the solution. So potential of the electrons which is given here 30k volt. It means 30 into 10 raised to the power 3 volt. Energy of the electrons equal to electron volt. So here E is equal to 3 into 10 raised to the power 4 electron volts. And E is equal to charge on an electron which is equal to 1.6 into 10 raised to the power minus 19 coulomb. So now let's focus on what we are being asked to find. So we are looking for the maximum frequency of the X-rays produced, which we call nu. To connect the energy of the electrons to the frequency of the X-rays, we are use the formula E equal to h nu. Alright. So we know the formula of the energy E is equal to h nu, where h is equal to Planck's constant. Their value is 6.626 into 10 raised to the power minus 34 joule second. So mu is equal to nu is equal to E by h. This means that if we know the energy of the X-rays photon, we can directly calculate its frequency by dividing by Planck's constant. So let's substitute the values into our formula. The energy E is given by charge of an electron, that is 1.6 into 10 raised to the power minus 19 into 3 into 10 raised to the power 4 divided by Planck's constant value. So when we solving this, you will be get nu is equal to 7.24 into 10 raised to the power 18 hertz. This is a very high frequency which is typical for X-rays. Hence the maximum frequency of X-rays produced is 7.24 into 10 raised to the power 18 hertz. Alright. Now let's focus on part B of this question, which asks for the minimum wavelength of the X-rays produced. The minimum wavelength corresponds to the highest energy that can be emitted when an electron loses all its kinetic energy in a single collision. So, formula lambda is equal to Cy nu. So, let's substitute the values. So, lambda equal to 3 into 10 raised to the power 8 divided by 7.24 into 10 raised to the power 18. So, when we solving this term, you will be get 4.14 into 10 raised to the power minus 11 meter. In nm, it will be 0.0414 nanometer. Hence, the minimum wavelength of X-rays produced is 0.0414 nanometer. The work function of cesium metal is 2.14 electron volt. When light of frequency 6 into 10 raised to the power 14 Hz is incident on the metal surface, photoemission of electrons occurs. What is the A. Maximum kinetic energy of the emitted electrons, B. Stopping potential, and C. Maximum speed of the emitted photoelectrons. Let's see the solution. So first, let's note the work function of cesium, which is given as 2.14 electron volts. The work function is the minimum energy needed to remove an electron from the surface of the metal. Frequency of light nu equal to 6.0 into 10 raised to the power 14 Hz. Higher frequency means higher photon energy. So let's write the photoelectric equation. Kmax equal to the h nu minus phi naught, where h is equal to Planck's constant, which is equal to 6.626 into 10 raised to the power minus 34 joule second. Alright. Now, first we know maximum kinetic energy, which is equal to h nu minus phi naught. So substitute the given values into the formula and solve it. You will be get the value of Kmax. Alright. So h nu 6.626 into 10 raised to the power minus 34 into 6 into 10 raised to the power 14 divided by 1.6 into 10 raised to the power minus 19 minus phi naught, that is 2.14. So solving this, you will be get 2.485 minus 2.140. It is equal to 0.345 electron volt. Right? This means that the most energetic electrons emitted from the cesium surface will have this amount of kinetic energy. Hence, the maximum kinetic energy of the emitted electron is 0.345 electron volts. This value tells us how much extra energy the electron have after escaping the metal surface. Now, for part B, we need to find the stopping potential, which is the minimum voltage required to stop the most energetic photoelectrons from reaching the anode. So the equation Kmax is equal to E V naught. So rearrange the equation to solve the stopping potential. So we have V naught equal to K by E, where Kmax is equal to 0.345 electron volt. So let's substitute the values into the equation. So we have V naught is equal to 0.345 into 1.6 into 10 raised to the power minus 19 divided by 1.6 into 10 raised to the power minus 19. So solving this, you will be get 0.345 volt. So stopping potential for cesium in this case is 0.345 volts. This means we need at least this much voltage to stop the fastest photoelectrons emitted from the surface. Now, uh, let's focus on part C of the question, which asks for the maximum speed of the emitted photoelectrons. We will call this speed V. This is the highest speed in an electron can have when it leaves the metal surface after absorbing energy from the incident light. So to find this speed, we use the formula for kinetic energy. Kmax is equal to 1 by 2 mv square, where m equal to mass of an electron, which is equal to 9.1 into 10 raised to the power minus 31 kg. Alright, so uh, let's focus on finding the maximum speed of the emitted photoelectrons. So v square equal to 2k divided by m. So substitute the values into the equation. So v square equal to 2 into 0.345 into 1.6 into 10 raised to the power minus 19 divided by 9.1 into 10 raised to the power minus 31. So solving this expression, alright, solving this expression, you will be get v square equal to 0.1104 into 10 raised to the power 12. So v equal to 3.323 into 10 raised to the power 5 meter per second. In kilometer, it will be 332.3 kilometer per second. So the maximum speed of the emitted photoelectrons is 332.3 kilometers per second. The photoelectric cutoff voltage in a certain experiment is 1.5 volt. What is the maximum kinetic energy of photoelectrons emitted? Alright, let's see the solution. So photoelectric cutoff voltage V naught equal to 1.5 volt. This value tells us the stopping potential required to halt the fastest photoelectrons. Now let's recall how to find the maximum kinetic energy of the emitted photoelectrons. The maximum kinetic energy is directly related to the stopping potential or cutoff voltage in the experiment. So Kmax is equal to EV naught, electron volt. So where E is equal to charge on an electron, that is equal to 1.6 into 10 raised to the power minus 19 coulomb. This is a fundamental constant in the physics. By plugging in the values for E and V naught, we can calculate the maximum kinetic energy numerically. So Kmax is equal to EV naught. So let's substitute the values into our formula, which is equal to 1.6 into 10 raised to the power minus 19 into 1.5. So solving this, you will be get 2.4 into 10 raised to the power minus 19 joule. Therefore, the maximum kinetic energy of the photoelectrons emitted in the given experiment is 2.4 into 10 raised to the power minus 19 joule. This result shows us how the stopping voltage directly determines the energy of the fastest electrons. Monochromatic light of wavelength 632.8 nanometer is produced by a helium neon laser. The power emitted is 9.42 meter watt. You have to find out A. Find the energy and momentum of each photon in the light beam. B. How many photons per second on an average arrive at a target irradiated by this beam? And last, how fast does a hydrogen atom have to travel in order to have the same momentum as that of the photon? Let's see the solution one by one. So first, let's note the wavelength of the light. It is given as 632.8 nanometer. or we can say 632.8 into 10 raised to the power minus 9 meter. Power emitted by the laser, which is equal to 9.42 milliwatt, which is equal to 9.42 into 10 raised to the power minus 3 watt. So Planck's constant H is equal to 6.626 into 10 raised to the power minus 34 joules second. Speed of light C equal to 3 into 10 raised to the power 8 meter per second. Mass of a hydrogen atom M equal to 1.66 into 10 raised to the power minus 27 kg. Alright, so these are the given terms. Now, since wavelength lambda equal to 632.8 nanometer, alright, so we need to convert in meter, so it will be 632.8 into 10 raised to the power minus 9 meter. The slope of the cutoff voltage V versus frequency nu of an incident light is given as V by nu, which is equal to 4.12 into 10 raised to the power minus 15 volt second. V is the related to the frequency by the equation. So h nu equal to electron volt. Alright. Now we know h nu is equal to electron volt, where E is the charge of an electron, and h is the Planck's constant. So E we know, and therefore h is equal to E into V by nu. So substitute the values into our formula. We multiply the charge of the electron 1.6 times 10 to the power of minus 19 coulombs by the given slope 4.12 times 10 to the power of minus 15 volt seconds. So solving this, you will get H. Alright, we can say 6.592 into 10 raised to the power minus 34 joule second. Alright. The threshold frequency for a certain metal is 3.3 into 10 raised to the power 14 Hertz. If the light of frequency 8.2 into 10 raised to the power 14 Hertz is incident on the metal, predict the cutoff voltage for the photoelectric emission. So here you have to find out the cutoff voltage. Let's see the solution. First, let's note the threshold frequency of the metal, which is 3.3 times 10 to the power 14 Hertz. This value tells us the lowest frequency of the light that can cause electrons to be emitted from this material. If the light has a frequency lower than this, no electrons will be emitted, no matter how intense of the light is. Next, the frequency of the incident light is given as 8.2 into 10 raised to the power 14 Hertz. This is much higher than the threshold frequency, so we can expect photoelectric emission to occur. So we know the charge on an electron, that is 1.6 into 10 raised to the power minus 19 coulomb, and Planck's constant 6.626 into 10 raised to the power minus 34 joules second. Cutoff voltage for the photoelectric emission from the metal is equal to V naught. Alright. Now to solve this, let's start by recalling the equation for the cutoff energy in the photoelectric effect. This equation relates the energy of the incident photons to the work function of the metal and the stopping potential or the cutoff voltage. So EV naught is equal to H into nu minus nu naught. So let's rearrange the equation and solve for V naught. You will be get correct value. So V naught equal to H into nu minus nu naught divided by E. So let's substitute the values and solve it. You will be get V naught equal to 2.0292 volt. Therefore, we can say cutoff voltage for photoelectric emission in this case is 2.0292 volts. This result shows us how the energy of the incident light minus the energy needed to the free the electrons determines the maximum kinetic energy and thus the stopping voltage. The work function for a certain metal is 4.2 electron volt. Will this metal give photoelectric emission for incident radiation of wavelength 330 nanometer? Let's see the solution. First, let's note the work function, which is given as 4.2 electron volts. Charge on an electron equal to 1.6 into 10 raised to the minus 19 coulomb. And Planck's constant H is equal to 6.6 into 10 raised to the minus 34 joules second. Wavelength of the incident radiation lambda equal to 330 nanometer. Speed of light 3 into 10 raised to the 8 meter per second. Alright. Now, let's find out how much energy each photon of the incident light carries. The energy of a photon depends on its wavelength. So we will use the formula for photon energy to start our calculation. So E equal to Hc by lambda, where lambda equal to 330 into 10 raised to the minus 9 meter. So let's substitute the values into the formula and solve it. You will be get E equal to 6.0 into 10 raised to the minus 19 joule. So equal to 6.0 into 10 raised to the minus 19 divided by 1.6 into 10 raised to the minus 19. So the power is cancel out. The remaining term is 3.76 electron volt. It can be observed that the energy of the incident radiation is less than the work function of the metal. This means the photon don't have enough energy to knock the electrons out of the metal. So the final answer is that no photoelectric emission will occur in this case. The incident light simply does not have enough energy to overcome the metal's work function. Light of frequency 7.21 into 10 raised to the power 14 Hz is the incident on a metal surface. Electrons with a maximum speed of 6.0 into 10 raised to the power 5 meter per second are ejected from the surface. What is the threshold frequency for photo emission of electrons? Let's see the solution. First, let's clarify the information given. The frequency of the incident photon nu equal to 7.21 into 10 raised to the power 14 Hz. Maximum speed of the electrons that is 6.0 into 10 raised to the power 5 meter per second. Planck's constant H is equal to 6.626 into 10 raised to the power minus 34 joule second. Mass of an electron m equal to 9.1 into 10 raised to the power minus 31 kg. For threshold frequency nu naught, the relation for kinetic energy is written as 1 by 2 mv square equal to h into nu minus nu naught. So nu naught is equal to nu minus mv square by 2h. Alright. Now the formula nu naught equal to nu minus mv square by 2h. So substitute the values into the formula. So nu naught equal to 7.21 into 10 raised to the power 14 minus 9.1 into 10 raised to the power minus 31 into 6 into 10 raised to the power 5 whole square and divided by 2 into 6.626 into 10 raised to the power minus 34. So solving this term, you will be get nu naught equal to 7.21 into 10 raised to the power 14 minus 2.472 into 10 raised to the power 14. So solving this, you will get nu naught equal to 4.738 into 10 raised to the power 14 Hz. Therefore, the threshold frequency for the photo emission of electrons is 4.738 into 10 raised to the power 14 Hz. Light of the wavelength 488 nanometer is produced by an argon laser which is used in the photoelectric effect. When light from this spectral line is incident on the emitter, the stopping potential of the photoelectrons is 0.38 volt. Find the work function of the material from which the emitter is made. Let's see the solution. So let's note the wavelength of the light used. The argon laser produces light with a wavelength of 488 nanometers. Stopping potential of the photoelectrons V naught equal to 0.38 volt, and 1 electron volt equal to 1.6 into 10 raised to power minus 19 joule. So stopping potential in electron volt is V naught equal to 0.38 divided by 1.6 into 10 raised to power minus 19 electron volt. Alright. Now Planck constant H equal to 6.6 into 10 raised to power minus 34 joule second. Charge on an electron equal to 1.6 into 10 raised to power minus 19 coulomb. Speed of light 3 into 10 raised to power 8 meter per second. Alright. And from Einstein photoelectric effect, we have the relation involving the work function phi naught of the material of the ammeter, as V naught is equal to Sc divided by lambda minus phi naught. So phi naught equal to Sc divided by lambda minus EV naught. Alright. Now substituting the values and solving this, you will be get phi naught. So phi naught equal to 2.54 minus 0.38 is equal to 2.16 electron volt. Therefore, the material with which the ammeter is made has the work function of 2.16 electron volt. What is the de Broglie wavelength of a bullet of mass 0.040 kg traveling at the speed of 1.0 km per second? B. A ball of mass 0.060 kg moving at a speed of 1.0 meter per second. And C. A dust particle of mass 1.0 into 10 raised to the power minus 9 kg drifting with a speed of 2.2 meter per second. Let's see the solution. So first, let's focus on part A. The mass of the bullet m equal to 0.040 kg and speed of the bullet v equal to 1 km per second. Planck's constant h equal to 6.6 into 10 raised to the power minus 34 joule second. De Broglie wavelength formula is what we will use next. It tells us that the wavelength lambda is equal to Planck's constant divided by the product of mass and velocity. So it will be lambda equal to h divided by mv. Alright. Now to solve this, we use the de Broglie wavelength formula, lambda equal to h divided by mv. Solving this, you will be get lambda equal to 1.65 into 10 raised to the power minus 35 meter. Mass of the ball m equal to 0.060 kg. Speed of the ball v equal to 1 meter per second. Alright. So now let's focus on part B. The de Broglie wavelength of the ball is given by the relation lambda equal to h by mv. So lambda equal to 6.6 into 10 raised to the power minus 34 divided by 0.060 into 1. So solving this, you will be get 1.1 into 10 raised to the power minus 34 meter. Now see, mass of the dust particle m equal to 1 into 10 raised to the power minus 9 kg and speed of the dust particle v equal to 2.2 meter per second. De Broglie wavelength of the dust particle is given by the relation, that is lambda equal to h by mv. So substitute the value and solve this, you will be get lambda equal to 3.0 into 10 raised to the power minus 25 meter. Show that the wavelength of electromagnetic radiation is equal to the de Broglie wavelength of its quantum. Let's see the solution. The momentum of a photon having energy h nu is given as P equal to h by lambda. So lambda equal to h by P, where lambda is wavelength of the electromagnetic radiation, c is the speed of light, h is Planck's constant. Now de Broglie wavelength of the photon is given as lambda equal to h divided by mv, but P equal to mass into velocity. So lambda equal to h by P. Alright. So lambda equal to h by P, and we know m is the mass of the photon, v is the velocity of the photon. So it can be inferred from equations first and second that the wavelength of the electromagnetic radiation is equal to the de Broglie wavelength of the photon. This result beautifully demonstrates the dual nature of light, showing it behaves both as a wave and particle. Thank you for your attention. I hope this lesson was helpful.